Welcome to the lecture on the continuation of analysis of guided structures. Now, in this session we are going to investigate the non-radiating dielectric guides, the propagation characteristics and the modes in such kinds of guides. So, typically the non-radiating dielectric guide is two parallel metal plates. So, this is a metal plate and so is this a metal plate. So, two metal plates within which a dielectric strip is inserted. So, this is a modification of the H guide in which the distance between the two ground planes or the two metal plates is less than lambda 0 by 2. So, this distance is less than lambda 0 by 2. So, the non-radiating dielectric guide is typically two metal plates, also called ground planes. So, this is a metal plate and so is this a metal plate, and within the two metal plates there is a dielectric strip. So, this is a dielectric strip and the distance between the two metal plates is constrained to be less than lambda 0 by 2. Okay. So, this is principally the difference between the non-radiating dielectric guide and the traditional H guide. So, this is the configuration of the non-radiating dielectric guide. Okay, so, this constraint that the distance between the metal plates is less than lambda 0 by 2 is what distinguishes the non-radiating dielectric guide. This constraint is what distinguishes the non-radiating dielectric guide from the H guide. The non-radiating dielectric guide is also characterized by very low loss properties up to even 94 gigahertz. Okay. So, it is because of the fact that the waves in this air region. So, these are the two air regions. So, here is air and here is air. So, the waves in the air region are evanescent in nature. Okay. So, let us investigate therefore, the characteristics and the modal characteristics of such guides which enable it to be a low loss propagating medium. So, the electromagnetic fields and propagation characteristics in the NRD can be completely described by using two sets of modes. Okay. So, let me draw the NRD guide once again. Let me draw the NRD guide once again. So, this is my NRD guide. Now, if I have my this as the y axis and this as the x axis. So, if I call this distance a and if I call this distance b, and the permittivity of this strip is epsilon r. Okay. So, we call this region 1 we call this as region 2 and we call this as region 3. So, these are the two, as we said that these are the two NRD ground planes or metal plates. So, this N stands for non radiating dielectric. So, in short we call this NRD. So, then the modes in the NRD are either LSM. LSM stands for longitudinal section or sectional magnetic. This mode is characterized by the absence of the magnetic field along the x direction. So, therefore, the normal component of the magnetic field which is normal to the dielectric strip is 0. In other words, the magnetic field is totally tangential to the dielectric air interface. Therefore, we can say that the magnetic field is totally confined or contained in the YZ plane. Such a magnetic field is called longitudinal sectional magnetic, because it is along the longitudinal section of the NRD. The other kind of mode is the longitudinal sectional electric. Longitudinal sectional electric, which is characterized by the fact that E x, again the normal component of the electric field on the dielectric air interface, which is E x is 0. So, therefore, for the LSE modes, the electric field is totally contained in the YZ plane, or it is totally contained in the on the surface of the dielectric with no normal component of the electric field along the x direction. So, you now see that both the LSM and the LSE modes have the UZ component. So, that means LSM mode has a Z component of the electric field and the magnetic field, and the LSE mode has a Z component of the electric field and the magnetic field. So, therefore, because the presence of the both the components of the electric and magnetic field along the Z direction, such modes are also referred, both these modes are also referred to as hybrid modes. This can be distinguished from the rectangular waveguide, where we either have the Z component of the electric field to be 0 or the Z component of the magnetic field to be 0. Okay, the TE to Z or the TM to Z modes. So, this distinguishes the non-radiating dielectric waveguide from the rectangular waveguide. So, in addition, you will see, you appreciate that basically what we are trying to do is that if we take the rectangular waveguide, if we compare this with the rectangular waveguide in this direction. Okay. So, in the case of the rectangular waveguide, so this was my A, this was my B. Okay. So, if I compare with this, you see that essentially what we are trying to do is that we are trying to minimize the conductor loss in these metallic walls, because there are 4 metallic walls of the rectangular waveguide. Such kinds of guides have or encounter high amount of loss, particularly at the millimeter wave frequencies or beyond. So, in order to combat such kind of loss, we have tried to eliminate 2 of the walls of the rectangular waveguide, and hence we came to this kind of an open guided wave structure. But if we just eliminate the two walls of the rectangular waveguide, we come to a parallel plate guide. If we just straight away eliminate the two walls of the waveguide. So, in the parallel plate waveguide, the radiation loss from from these two ends would be significant, and so also would be the condition with the H guide. So, this is the parallel plate waveguide. Okay. And if we also compare this with the H guide, where this is the dielectric strip again with, so this is epsilon r, with this distance a, there is no constraint on this distance a. Okay. So, under such a condition also, what essentially happens is that we have attempted in the H guide, you look, it is in the shape of an inverted H, that is why it is called an H guide. Okay. So, in this case we have attempted to confine the electromagnetic field inside the dielectric strip. So, if I increase the permittivity of epsilon r, if I increase this permittivity, okay, the more the permittivity, the idea is the more confined will be the modes inside the dielectric strip, and the radiation loss which is present in the parallel plate waveguide can be counteracted or can be reduced. That is the philosophy, that was the philosophy of the development of the H guide. So, to combat essentially the radiation loss from two sides of the parallel plate waveguide by inserting a dielectric strip, and therefore, the higher the permittivity of the dielectric strip, the mode confinement inside the strip. But there are a number of problems to the H guide. That is one problem is that we are dependent on increasing the permittivity of the dielectric strip in order to counteract the radiation loss from the two sides. So, increasing permittivity of the dielectric strip entails a number of problems. First of all, that high permittivity dielectric strips are brittle. So, for mill grade or space grade applications where the circuit components are subjected to violent G forces in many cases, so and violent like harsh environments. So, the H guide may not be like it may not be suitable, because the high permittivity strips are brittle. Secondly, when you want to stick the high permittivity dielectric strip to a metallic surface, there are invisible air gaps. So, these are air gaps. We need to be careful of such a case, because we are dealing with in many cases millimeter wave propagation. Okay. Such air gaps are not visible to the naked eye, but they are there and they will interfere. They are also here. So, these are the air gaps, they are also here, and they will alter the modal characteristics of the H guide. So, some of these reasons actually prevented the future development of the H guide, in addition to the fact that the radiation loss from the two sides of the H guide were still not acceptable. So, in order to develop an improved version of the H guide, we came to the NRD guide, in which the only constraint or the only difference with the H guide was this distance a being less than lambda 0 by 2. Because this distance a is less than lambda 0 by 2, so this region offers a cutoff. Okay. So, this is a cutoff region for the wave, and therefore, the waves in this region are evanescent. Okay. So, because no electromagnetic wave can travel if the distance between the two metallic plates is less than lambda 0 by 2. We need a minimum distance of lambda 0 by 2 for the electromagnetic wave to travel. Okay. We need this as minimum lambda 0 by 2. So, therefore, when we are offering a below cutoff operation in the air region, the waves in this region, the waves in region 1 and region 3 becomes evanescent, and then we are not dependent on the permittivity or increasing the permittivity of the dielectric strip to a very high value in order to counteract the radiation from the two sides of the NRD guide. So, this principally distinguishes the NRD guide from the H guide, that even like a moderate value of this epsilon r a moderate value of the permittivity of the dielectric strip would actually result in a low loss guided structure way up to 94 gigahertz and even beyond. But we have to contend with more complex modes like the LSM and the LSE modes of the guide, which we said as hybrid in the sense that they possess both the Z component of the electric and the magnetic field, unlike the rectangular waveguide. Okay, so a more complex guided structure. In addition, we are going to come to this situation that the LSM mode is more preferred for NRD mode operation because of its lower loss compared to the LSE mode. However, the LSE mode has a lower cutoff than the LSM mode. We are going to come to these aspects. So, therefore, this complicates matters for the NRD, because we have to use a mode which is the LSM, which has a higher cutoff than the LSE. We did not do that for the rectangular waveguide. The T01 mode which we used is the dominant mode, and it has the lowest cutoff, and we are using that mode. Okay. So, therefore, there is no question of using components like mode suppressors, but the question of such components arises because the LSE mode is the dominant mode. Okay, the principal LSE 00 mode is the dominant mode compared to the often used LSM 01 mode, which is the higher order mode. But we are constrained to use the LSM 01 mode, which is the higher order mode, because it is less lossy than the LSE 00 mode. And if the like if the characteristics or the design demands that the LSE 00 mode has been appreciably excited, because it is dominant, it is the dominant mode. So, it has the propensity or it has the tendency to be excited at curvatures or discontinuities. Okay. So, if the excitation of the LSE 00 mode is appreciable, then it has to be suppressed, and such kind of suppression has to be done by components called mode suppressors. So, the mode suppressor would essentially stop the LSE mode and enable the propagation of the LSM mode. Okay. So, let us now review the characteristics, go in a little bit more details on the features of the NRD guide. So, as we said, for the first set of modes, the magnetic field is entirely parallel to the air dielectric interface, and that is known as the LSM MN mode. Okay. As we said, longitudinal sectional magnetic. Similarly, for the second, the electric field completely lies in a plane parallel to the air dielectric interface, and that is called the LSE MN mode. We are going to come to what the MN denotes. So, that is the longitudinal sectional electric. So, here the magnetic field is entirely parallel to the air dielectric interface, and here the electric field is entirely parallel to the air dielectric interface. The subscript M, so this subscript describes the transverse variation of fields inside the dielectric strip. So, that means that this is the wave number which describes the variation of the fields inside this strip. So, as we marked this one was my y. So, this was my x. So, this describes the transverse variation of the fields along the x direction inside the strip. This can be either of the cosinusoidal or the sinusoidal type. So, inside this strip the fields can vary, either it can, the variation can be even or a cosinusoidal type, or odd, which is the sinusoidal type. For both the LSM and the LSE modes, the corresponding potential functions can possess either a cosinusoidal variation or a sinusoidal variation inside the dielectric region. So, here the potential function can have either a cosinusoidal or a sinusoidal distribution, and therefore, it can have a even or odd symmetry about the center. So, for the cosinusoidal variation it will be an even mode, and for the sinusoidal variation, as we said, it will be the odd mode. Okay. So, LSM even or LSM odd or LSE even or LSE odd. So, the other subscript n, which is this subscript, describes the variation of the standing wave pattern between the ground planes of the NRD. So, it describes the variation of the fields in this direction. Okay. So, M is along this direction, M is along that direction. So, let us put it like that. Okay. So, that describes the modal numbers or the eigen numbers m and n for both the LSM and LSE modes. So, therefore, we also discussed that the modes in the NRD possess both the electric and magnetic field components along the longitudinal propagation direction, and therefore, they are hybrid in nature. However, one should note that the TEM mode propagation is not possible in the NRD as in the parallel plate guide because of the presence of the dielectric strip. So, the TEM mode propagation is not a possibility in the NRD guide. So, there is no TEM mode propagation in the NRD guide. We have also discussed, and it is important to appreciate, that the essential difference between an NRD and an H guide, the H guide which suffers from considerable leakage and radiation loss, okay, it is the restriction in the distance between the ground planes to less than half a free space wavelength in the NRD. So, in the NRD this distance between the ground planes is less than lambda 0 by 2 for the NRD, whereas no such restriction happens or is there in the H guide. This essentially distinguishes the H guide from the NRD. So, as such, we have also seen that the fields in the air region in the NRD, which are region 1 and region 3. If we go back to the figure, in these two regions, in the air regions, this region and this region, they are below cutoff and are evanescent in nature. Okay. So, the fields in these two regions are below cutoff and they are evanescent in nature. So, region 1, region 2, region 3. Okay. So, the fields in region 1 and region 3 are evanescent and below cutoff. However, the presence of the dielectric in region 2 removes the cutoff condition between the ground planes and causes the EM waves to propagate down the structure, essentially confined within the dielectric strip. So, the presence of the dielectric will remove the cutoff condition and enable the waves to propagate inside the dielectric strip. Okay. Because of this, leakage and radiation losses at curved sections or discontinuities are almost non-existent in the NRD. This is a very important point to note. This is a very important point to note that this is the principal cause of the low loss and low leakage properties of the NRD. Also, the electric field profile of the LSM-01 mode, which is commonly used as the principal waveguiding mode in most applications, is essentially parallel to the ground planes. So, if we note the LSM-01 mode, essentially you have this, essentially we have this kind of a structure. So, if I draw the field properties of the LSM-01 mode, so this will be the electric field. And if I draw the magnetic field, this is the magnetic field. So, essentially because the electric field is tangential to the ground plane, these are the two ground planes. Because the electric field is tangential to the ground plane, okay, it is in this direction. So, therefore, the transmission loss of the guide is reduced, okay, essentially because you see that the magnetic field is normal to the ground plane. So, essentially there is no current induced on the ground plane due to the magnetic field, which reduces the transmission loss of the NRD. So, this property is very important, that this decreases the fact of the electric field profile of the LSM-01 mode being the most popular mode in most NRD applications, being essentially parallel to the ground planes, decreases the transmission loss of the guide significantly and makes it an extremely low loss waveguiding medium at millimeter wave frequencies. Okay. So, this has to be understood from the perspective of the field profile. The field profile, the low loss characteristics of the LSM-01 mode has to be understood from the field profile of the LSM-01 mode. Okay. This fact, coupled with the fact that the NRD based discontinuities are purely reactive due to their non-radiative nature, presents some unique and sought after advantages in millimeter wave component design. Okay, because there is no radiation, so the NRD based discontinuities are purely reactive, and therefore, this presents like this is a very desirable characteristics in the millimeter wave component design. Okay. So, let us stop here, we are going to continue from here.